Okay, good morning. So could you sleep last night? Yes? Then why did we give that problem sheet? It was meant for, okay, good. You can compensate it tonight. Okay, so could you attempt the problem that we had discussed? That's we wanted to build a data structure for an arrangement of points, a planar geometric structure which has different kinds of entities, vertices, edges connecting the vertices, and faces as bounded by the vertices. And so we need to create a data structure which will represent these, and these are some of the sample operations that we can do on that data structure. So let's take an example. We can give some names here as well, say E1, E2, E3, E4, E5, E6, E7, E8, E9. So could you suggest a data structure to represent this? We have edges, we have vertices, we have edges, and we have faces. 3 types of entities, and we need to represent this structure and make sure that these kind of operations can be, that is, I can do enumeration, I can do iteration in multiple, given a face I can walk around that face in counterclockwise manner. If I am at a vertex, if I am at a face, then I can find an adjacent face. If I am at a vertex, then I can go around the vertex and find the edges that meet at that vertex point. So what would you suggest should be the data? How should we represent this information? Pardon? These are not the only operations, these are indicative operations. These are indicative operations, so this just give you some idea of how this can be done, and this is a geometric structure. So this is an arrangement of points. So this is not a schematic. This is not a schematic graph. This is a physical graph. So this is like the Google Map graph we are talking about. So these points are physically fixed. So they have coordinates naturally because it's a geometric structure, as we said. It's a planar geometric structure. So it's not like a schematic that we say that okay, vertices could be anywhere. It's just the relationship that matters. Yes, ma'am. Okay, please. You would like to come and present here?
Take vertices for each face, like represent it. I forgot actually what you call that graph. Take vertices for each face, so and represent it as a 3-dimensional array.
I mean, could you just
you have an adjacency kind of matrix for faces.
Okay.
So there are 4 vertices actually, like F1, F2, F3, F4.
Okay.
And 4 by 4 by some n.
Okay, let me write it here itself, I'll redraw. So what you are saying is we have F1, F2, F3, F4.
Yeah,
These are the 4 rows. And
4 columns.
what do we keep on the columns?
We have 3-dimensional array, and each element will be an array with the surrounding edges, or actually the border.
You have a 3-dimensional array.
Yes.
So you have a triplet,
Yeah.
right? So 3-dimensional array means every element is a triplet.
Yeah, actually.
Okay. So what are these 3 components?
The faces F1, F2, and the edge EI between, that is, between these 2 faces, or rather dividing these faces. So you may have multiple edges between 2 faces.
So you'll have multiple such triplets.
And the last column represents the ordering, that is.
No, you have a 3-dimensional representation.
Yes.
So every element
Yeah.
has 3
Yes.
components,
Yes.
right? So you're saying one component is one face,
Yeah,
other component is, so there are 2 face axes, and on the face axis you show what is the common edge.
Yes.
Right?
There may be multiple edges, like F1, between F1 and F2.
So there will be multiple entries for that.
Yes.
So we will have F1, F2, E4, we will have F1, F2, E3.
The size will be, the 3rd dimension size will be number of edges plus 1.
Whatever the size is, that's the second question. First is the representation and the correctness.
No, I'm using the last column for ordering so that I can have a clockwise.
What do you mean
and
last column? It's a 3-dimensional,
Sorry,
so there is
sorry,
no last
that is
column.
For 3rd dimension element, I'm talking about the last element.
Then where does the edge go?
No, all these.
What is the first component? 3 components you have.
Yes, yes.
So what is the first component?
First 2 are faces.
First 2 are faces.
Yeah.
And the third one?
3rd dimension gives both the informations, like the edges between the faces and the ordering of that.
How can you have ordering?
Because I should be able to.
You should be,
Yeah.
but is that representation taking care of this?
That's what anti-clockwise ordering can I have for each face. One element will be the
order
ordering.
itself.
Yeah.
That is,
No, the
That-
number of the
you want to
edge in the
keep number of edges.
No, sir.
No, so let's say there's an example. So if you can just tell us the triplets.
Like if you have edge.
So let's say let's start with a simpler one, not multiple edges. Say F1, F3. So F1, F3, and what do I write?
Yeah, E6. That is 3, 1, 0, 0, 1, 0, 0, 0 will be 3.
0, 0, 0.
No. 0, 0, 0th element.
Yeah, that is F1, F2.
And E3.
F1, F2.
What is that? E6, yeah, E6.
E6, right.
There is only one edge, so all other entries will be zeros.
So it is F1, F3, E6.
A6, F1, F3, 0, F1, F3, if depending on the dimension.
F1, F3.
0, because we don't have any other edges.
So as many edges are there, you'll list all of that.
The total number of edges
Total
will be
number
the
of
size of
edges
the 3rd dimension.
Yes, but that certainly does not give us neither the, it gives us the adjacency of faces,
The last 2 will be.
but it does not give us the edges around a vertex. There's no vertex information here. Yes?
Sir, if we maintain a single face as a list of adjacency edges, adjacency edge list, say F1 is represented as E1, E3, E4, E6, that we can maintain, then we can maintain a separate list of such faces. Now here for looking for the adjacent faces, we have to watch some time. But Madam's approach also we can little bit enhance, like if we represent one face as a one adjacency matrix, where only the vertex V1, V2 are stored like that.
No, just be clear. your every A face has a list of edges going in that order.
No, madam's first triplet, it should be if it F1, Fi.
So you have this triplet also.
No, in madam's approach, maybe modification I am just saying, if we maintain that one as a Fi, then Vj, Vk. Vj, Vk are representing the edges.
No, tell me on this face F3, what do I write?
F3. Now here we will write say F3. Then E6, that is P7, P5, P7.
Oh, not edges, the vertices.
Not vertices.
V5,
V7.
V7.
Then again another entry F3, V5 and V possibly that was 8. P6.
V6.
P6. Then another entry that F3, V6, P7. So that one plane is representing that phase 3. So in the next plane we can find out but searching time.
Yeah, so you are fragmenting. I mean, this does not have the edge information.
But this V5, V6, that is representing the edges. The pair of vertices, they are representing the edges.
Yes, but how do I find the adjacent face from here?
So that's why that searching will be needed for within different planes.
Any other suggestions?
Sir.
Yes. Yeah, you can have anything. Anything is open field.
Excuse me?
Okay. Face. So for F3. Face. Then? Which part? Which vertex? Any vertex. V5. Then? There is no question of visiting. There is no dynamics. This is a representation. This is a representation. So first the representation, then we will do the adjacency list of this graph.
And that graph will contain 4 headers. First header will be F1, F2, F3 and F4.
See the adjacency list you said. Adjacency list, what does it give? It tells you which vertex is adjacent to what other vertex. Right? The information about the edge is implicit and the information about the face does not exist. Right?
We are addressing the node in that way.
Yeah, but
We will address the node in that way that one of the part of the node will be representing face.
how do you find out the order then? You cannot.
Now we can maintain in a list.
Maintain?
Any of the nodes we have consider as the first node in the list.
Right.
Then we are going to traverse it to. We can traverse it by either any adjacent node. Either it will be towards the node should consist
See, you should understand that if you are making a data structure and some operations are suggested, that does not mean that you will pre-compute all of that and keep in the data structure and that becomes your data structure. Right. So this is not turning out to be a data structure. You are just you are enumerating all that is asked for and just storing that result so that you can look up. Okay? That way you will not be able to. Yes.
Excuse me, sir. So we have to maintain a list for phases.
List for faces.
So each and every phase pointing on adjacency matrix. That matrix have E1, E2. That each and every adjacency matrix having the vertices and edges of that phases.
Okay.
So that means it is easily accessed for each and every.
Fine.
phase.
Given a vertex, how do you find the edges that meet at that point?
Adjacency matrix using the adjacency.
That's corresponding to that phase. So this vertex participate in 4 phases. Right?
vertex that is available in all the
Four phases. So you will have to look for vertex V5 in the adjacency matrix of each of these phases. Right? So it will.
complicate.
You can understand the complexity that will turn out to be. Yes, sir. pointer of array or array of pointers you are meaning, array of pointers. That particular vertex. Okay. So if I try to write, let me use a different color. So if we are talking about V7, then we have a list of V7. So E9, E6, E3. Then, right? So F2 we will write 4. Not how many? You mean the vertices on that? Okay. You can dig out with some possibility, right? But certainly this one you have directly represented. Adjacency of face you cannot figure out from here. Any other?
Sir, I made a change to the solution.
I mean, let's hear the new persons at the back, please.
Sir, if we organize this graph according to the age-wise.
According to?
Age-wise.
Age-wise, right?
If age is to be there, every age has at the most 2 faces.
Right.
So, for example, E1 is the age. So I would like to make the tuple. E1, it's a node and adjacent faces.
E1.
Yeah, E1.
E1.
Nodes are V1 and V2.
V1, V2.
And faces are F1 and F4.
Faces are F1, F4.
Yeah.
Right?
Age-wise, that graph can be organized. And as many ages we can add according with these attributes.
Right, great. We'll find this out. But how do we find the vertices that, the edges that meet at a vertex?
Yes.
Edges that meet at a vertex? Or how do we go in the counterclockwise order?
That is not.
You know, it's, yes.
Sir, we'll take two-dimensional array.
We'll come back to you, don't worry.
Sir, we will take two-dimensional array.
Okay.
One to represent the graph, one to represent the faces.
One to represent the graph, one to represent the faces. Okay.
One will have the edges and the vertex. Another will be having faces and what all the edges comes in the faces, in that face.
One will have the faces and?
Yeah, one first array will have the face 1, what all the edges comes in the around that face. Another one is the actual represent the graph.
How do you find adjacent faces?
Adjacent faces, you will find out, you will go through that, say for example in the first array we will go with F1. If it is what all the edges you will find out.
So mind you, it's not mentioned here, but we have made it very clear that the contract is not only about what you can do, but it comes with a cost. Right? What you are saying is a linear cost, right? It needs going through that. So obviously we would want this to happen in either constant cost or what we commonly say is the output complexity of the problem. That is, the cost should be proportional to the output that you generate. I mean, the challenge here is not to be able to represent, because certainly, I mean, many of the representations that you are talking about would certainly work. But the problem is, how do you get performance in that? How do you make this constant time or proportional to the output complexity? So there are several ideas, but let me just outline one, because we cannot spend a lot more time on this. So let me just redraw this graph and try to work on some of the ideas. and these are the faces. We will make some, to start with, we will make some observations. The key observation in this is, say if we start with the first objective, that we should be able to work around a face in a counterclockwise order. So that's basically going on the list of the edges. Right. Now, if you look into, say, this face F and F1 and the face F3, if you go in the counterclockwise order, this is this edge, this edge, this edge, so you go from V5 to V7. Right? That is the order in which, because you will go counterclockwise. Now go counterclockwise on F3. What will it be? It will be V6, V7, V7, V5. So if you go on F1, the edge actually goes from V5 to V7. If you go on V3, it goes from V7 to V5. And in most most of the representations that is being suggested, if you see that this is a core problem which will need to be solved, because whichever order you keep it, the other ordering will be required, and you will need to do a linear search there. Right. So this problem has one of the very interesting solution, that all that you do is, to represent an edge, you split it into two edges. Kind of, you can call it half edge. So we'll say any edge here is a pair of edges, and half edges are directed. Original edges are not directed. What is the advantage? Advantage is now I can do half edges in the order of a face. Right? Once you identify that, then rest of the problem is very simple. Because then you just chart out the information that you need to keep. What do we need so there are three entities. So how do you represent a vertex? What are the information you need for the vertex? Certainly you need the coordinate, which is because it's a geometric problem. And let us just number these edges. So let's call them E11, E12, E21, E22, E31, E32, E41, E42, E51, E52, E61, E62, E71, E72, E81, E82, E91, E92. So every edge you have a pair, or you can say there is a twin edge, so you number them as 1, 2. So you keep the vertex and say keep some edge which goes out of this vertex. The basic relationship with the vertex and the edge. Right? To keep a face, you keep one of the edges. Simple. Now, for an edge, that is your basic entity, because that gives you the traversal. So keep, say, the origin, so you keep the twin keep a face. Which face do you keep? The face that is on the left, because your traversal is counterclockwise. You keep a next. You keep a previous. I'm sorry, we should also keep as origin and the other side, V2. Okay? We keep this information. Intention is simple, that edges now give you all the information. So you need to know where does it go, what is the next edge, what is the previous one, so that you can get this circuit, and what is the phase that it is associated with. Right? These are linear. Right? The data structure is linear. All these items are linear. Right? It's a linear in the input. How do you do the first one? You have the phase. Phase gives you one of the edges. Start from that edge. Do next, 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 till you come back to this edge. If you start with F1, F1 has an edge, this edge E11. The next of that is E21, next of that, next of that, next of that. You will eventually come back to this edge when your counterclockwise traversal is over. Right? I think I missed out on one key information. I will also keep the twin, the pair, the edge that it pairs with. I will also keep a pointer to that twin edge. So the first part is easy, right? Oh, I have written? Okay. I'm sorry. So that basically is the twin.
Sir, but for the phase F4, we have clockwise order of all the edges. If you consider phase F4, the order of edges is clockwise.
Phase F4, the order of edges is?
It's clockwise.
How do you know? It's an unbounded space. Your sense of clockwise and anti-clockwise is with respect to a bounded space. Right? So you really don't care about what order you get for F4. Whatever order results is the counterclockwise one for that. You can you can enforce that by, if you really bound this in a space, then you will find that, because that other sense is not there. How do you do the next one, second one? Suppose you know phase F4. Can you find an adjacent phase? Or let's take something else, because F4 is practically adjacent to everybody. Let's say F1. At any point, a phase has an edge, and the twin of that phase is the phase of an adjacent edge. So finding an adjacent phase is taking the twin and finding the phase of that twin. So if I have, say, phase F1, this E11, the adjacent phase is E12, twin phase is E12. E12 is a phase for F4. So you can find out the adjacent phase. In other adjacent phases, you can traverse using the first technique, and You do the same on every face, you'll be able to enumerate the faces. How do you get all the vertices, all the edges at a vertex? Say at V7, how can you get all the edges that meet at V7? Let's represent V7. Let's say V7. What does V7 need? It has some coordinates, which is immaterial right now, and it has one edge that originates from here, say E92. How do you find all the edges that meet at this point? V92
V92 is represented as the vertex.
V92 is originating from V7, so we know that.
So V7 is represented for each and every edge.
Right. But how do I find it out in constant time or in output time? Yes.
Each and every edge is represented by vertex is also mentioned there.
Right.
So here E92, using E92 you go and fetch the vertex V7.
The vertex V7, given the vertex V7, I want to find these edges that meet at this vertex.
V7 is represented in all the edge representation.
True. How do I find it out? If I search them, it's linear. Certainly I do not want to do that. Yes, ma'am? Just check the mic.
Take the edge incident on that. It's twins adjacent edge you take. That will be
Pardon? Take which edge?
E91.
V7
E92.
has E92.
Yeah, E92. From E92 you go to E91 because you have a twin saved.
Right.
E91's adjacent edge. That
E91's vertex is V1.
Next. No, E91's next.
E91's next is E81.
Yeah, that is
Right.
that is one adjacent, that is incident edge.
Right.
Take its again twins edge next. Go on doing that until you reach the.
Got it? So it's you have got one edge, so you take its twin, that's constant time. The twin's next edge will certainly, you'll come back to this. If you take twin and follow the edge, you're coming back to the same vertex. So if you do the next edge is what goes out of that vertex, so you get the next edge. And just keep on doing that. Take its twin to the next edge, you'll eventually come back here. So the beauty of this representation is that you have chosen to just represent the cycles in the face with separate edges, and it eventually also maintains the ordering of the edges around a vertex. It maintains all the connectivity information that this kind of a structure will present. So it's an interesting idea. If you get into any kind of geometric problem solving, you'll find that this core idea of representing, PPC was talking about Google Maps being very large and being solved. So naturally you cannot solve them by that brute force representation. So these are some of the techniques that the Google Maps use to find information of how you can route a path, because routing path is basically finding face adjacencies so that you can go from here to here to here and so on. Okay. So this was just a example that and I'm not this is worked out at length in the in the slides that follow. So, in case you want to refer to it in future, you can do that. Let us move on. Let us quickly take a look at a couple of very simple problems, and because we wanted to discuss sorting and searching, and certainly there is nothing to discuss in sorting and searching. You already knew all sorting algorithms almost, right? And then we have already discussed the generalization of that, what is the recursive definition structure from which all sorting algorithms can be generalized. So, we will take a look into some of the sorting and searching problems which are very similar to what we have done, but just to see how nice design strategies could be employed there. So, this problem says that they have a searching multiple items in a list. That is, it's just a generalization of the search problem, where when we talk about search, what do we say? That I have a given collection of items, possibly integers, that does not matter here, positive integers you can assume, and you are given an item and you will have to specify whether the item exists in the list. If it does, you return that, and possibly it has other associated information, and if it does not exist, you say that it could not be found. So, we are just generalizing it little bit, saying that you do not have one search key, but you have a set of search keys, and we want an answer to that whole thing, right. So, find a set of elements in an unordered set of list of elements. L is that such a set of n distinct integers. This is not ordered in any fashion, and K is my query, is a list of m distinct integers, and we want to find out the existence of elements of K in the list L. These are, for all these problems, this is what we want to answer. Just attempts. How do we do this? A very simple problem, right? How do we do this? The first one is pretty, I mean, n squared. I mean, the first thing is how do you do it? Then comes the question of, how do you do it, whether it terminates, whether it's correct. Then comes the question of performance. Anybody who would like to? I think I would like to encourage others who, possibly the interaction is somehow getting limited to about 15 people. So, I would like to encourage others to start responding. Yes?
Sir, we will compare K element with the current position of the element of your list, which is in list L. So, every time we will move one position ahead, and at that time we will compare all the elements, that is K element with that specific element in the list L.
What is the complexity?
Sir, K into N.
K is the name of the list. You mean M into N?
Okay, sorry, yeah,
M into N. I would put that in more simple terms. I will not do so much. I have a single element search function. I'll call it M number of times. That's it, right? I would not complicate by making modifications there. So, I'll apply it M number of times. Done. So, that is, we have got the first solution. So, it can be solved. Initial solution is been obtained. So, it is order M into N. Right? So, can we do better than this? Now, if M is constant, then this still may be okay, because we will still have an order n algorithm. But it is not specified, M may not be constant, M may be a function of n. Can we do anything better than this? We can't do anything better? We go? big O of m plus n. How you get that? If m is a function of n, how do you get that? That means you are saying that if I have n elements to search, I can search them in linear time, right? So, is that anything else that we can do? We can initially sort the entire array, okay? And then do m different binary searches. Good. So, what will that cost? Order of m plus n, n log n, and m log n, right? This is what we will get. First one is to sort the array L, and the second for m searches, right? Agreed? Good. Anything better than this? Could you get the mic here?
We could divide the list L into two parts, and then suppose we have two elements in M. So take the first element, search in the first half, and take the second element, search in the next half. So if you find both of them, then we don't need to do again, we don't need to search for 4 in the next half.
Excellent. But there's a possibility that we find none of them because each one exists in the other half, right? What do we do about that? But that, I mean, your thought has a good clue to what possibly we can do to improve this.
Sir,
Can we try to do anything better than this? Yes,
sir,
please.
first we sort all the n integer elements, then we form the block of some group of element and form the indexing of that. Then we, what are the element that we want to search? First we compare that with the index. If it is there, then we can search within that particular block.
We are in not, okay, I should have specified that we are in the paradigm of comparison based searching. So, if you hash it becomes a totally different story altogether, because then your single element search itself is not log n, right? If you do a radixing or you do some kind of hashing, then your single element search itself will be something different. So, we are talking about improvements on binary search or comparison based search.
Sir.
Yes?
Sir, sort the list L, then sort the list K, find the median of list K, and then for that median, where that median is, whether it is in the list L or not.
Then?
And then when the median is found.
So now we have two cases. The median is in L.
Median is in L. Then find all the left element to left of median in the left list of L.
Could you avoid finding this median, because median does not have any role here, right?
Median, that is just
once you have sorted L, median does not have much role.
No. Sort L as it is.
So what you are adding is sorting K.
Sort K, find the median.
Right. Now, after you have sorted K, can you improve your search by using that knowledge that K is sorted?
Yes. Median, if we find the median, then all the elements to the left of the median can be found out in the list L where it was found, and left of that one.
Yes. True.
So that way it can be more
yes,
made more efficient.
that could be a strategy.
Sir, excuse me, sir.
Yes, please.
Sir, in the M list, you have to directly compare M values.
So here we had plus I do not know what what your remaining part of the strategy will cost. Yes, please.
Sir, in the unordered list, so unordered list L, we directly compare M elements directly. We have to maintain a flag 0, all zeros initially. So if it is found, you have to set 1. So next you have to move 1 right shift, then again we have to compare.
That's the first strategy.
That is M plus N. It contains only M minus N minus M.
No, you are forgetting that at every stage you will do M comparisons. At every stage you will do M comparisons.
M comparisons.
So it's not
right
M plus N, it is M times N. You will do M comparison at every stage and slide it N times.
Not
so it is
N times, sir. So that is N minus M into N, something like that.
Yes, but it's order of N.
Hello.
I mean, I think nice ideas are coming out. We can, for example, look at, suppose this
Hello,
is
sir.
L, let's say.
Sir.
Yes, please.
Sir, we sort the K and L separately.
K and L separately. Let me just write that sorted order.
So these two lists.
This is L, this is K. Yes.
Then
Go
we
ahead.
start from K.
Sorted.
First element of K.
Right.
Then we compare with from the first element of L till 9.
First element of L.
L. We then increment that the pointer which is pointing to the first element of L.
But you have already sorted L.
Then we compare the first element of K with the elements of the L.
Elements in linear order?
Yeah.
Then why did you sort it? See, you can, if you look into, I mean, this is why
Can we compare the middle elements of both the arrays? And
you can, but what does it give us?
And restrict the list.
Which function? Taylor function.
We can compute the failure function so that how many times we will skip when we are comparing with that L and K, first of all, without sorting. Then it will take big of M plus N.
M plus N.
Yeah. Not big of N. Time complexity.
This one?
Yeah.
You're still on this?
Yeah.
Right?
Yeah.
Then you can sort in linear time. Right?
Yeah, we can have.
I mean, M can be N, so you're practically sorting in linear time. So that's a counter logic. Yeah, okay. I mean, some of the strategies, I think some of you are close to a better strategy. Suppose if this is the instance, I have sorted both of them. So I have got this, I have got this, and then I'm looking for N, 9. So I can do a binary search and I'll get 9 here. Right. Now the point is, once I have found this, or I have not found it, if I have not found it, then I know the position where it was expected. Then, when I look for 14, I do not need to look at this part of the array. Right? So I can only do on the remaining part. And wherever it was not found, all remaining elements can be looked at this, only this part of the array. Right? So this could be a better strategy. The analysis is up to you to do. If you get stuck, please consult the TAs. They'll. Okay, so let's move on. Another sorting problem. Very simple problem. I think this we will get in a minute, surely. We have an almost sorted array. What we mean by almost sorted is every element is displaced. Array is sorted, and not every element. Array is sorted, and some elements that you do not know have been displaced by one position. So it has been swapped with one of its neighbors. So it's one position away from where it should have been. And some elements are at the right position. That's our definition of almost sorted. I mean, it's not an universal definition, we are just saying that. If that be the definition of an almost sorted array, and you are given such an almost sorted array, you can see this is in non-decreasing order, and there's an inversion here. 1 should have been here, 12 should have been here, so there's an inversion. There's another inversion here. 44 should have been here, 55 should have been here, they have been, right? So this is almost sorted. Now, how do you search this array? You are given an element, you have to search this array. Yes, there is the green shard. Please speak on the mic.
We can apply insertion sort for this.
We can apply insertion sort for this.
Yes. Means the insertion sort is this technique where this one, you choose this element from this left side, you keep one element out and you pick the element from the second position, actually second elements onwards, and you keep comparing to the left.
Yes. I mean, you can apply insertion sort, you can apply any kind of sort, that will work.
But insertion sort takes order of n time here.
Yes.
Actually, order of n.
True. So your query time is order n, right?
Yes.
Can you do better than that? If this was sorted, what time we would have taken? If this were not almost sorted, totally sorted, then given an element, how much time we would have taken? Log n, right? So order n is too expansive. It's just, it has that salted pepper noise, as we say, kind of. Use a binary search. Yeah, but binary search needs a guarantee that wherever I split, all elements to the left are, say, smaller, and all elements to the right are, say, larger.
After find that location, the next element you have to compare.
What?
Find the mid. So mid location, then compare the adjacent values, whether it is found or not.
Agreed? So it's a simple strategy that can work, that all that we do is, we do the binary search, but just modify it. We do the divide. But instead of taking the left part of the array or the right part of the array, if I am to take the left part of the array, I also choose one element from the right. Because one element could have been misplaced. If I have to take the right part of the array, then I'll also take the left part. One element on the left. So instead of taking n by 2, I take n by 2 plus one element and do the, because that will guarantee that the element is in that, right? So,
sir,
yes,
we just search the only one element or more than one element?
One element. This is searching for one element, but the array is almost sorted.
Okay.
Searching for more elements was the earlier problem.
Okay, then log n plus 2.
Okay, so if we and you can analyze, the recurrence would look different now, but you could analyze and show that it will still be order log n. Of course, the constant will be somewhat different. You can just work it out. Constant would be a little bigger. And you could also explore what will happen if I extend this definition of being almost sorted to not having one inversion, but having k inversions. Locally, k inversions have been allowed. So an element is away from its position not by one location, but by k locations. Right? So that gives you a very general interesting problem of sorting almost sorted arrays. So that's again for the workout in the afternoon. You just work it out and show. If you have a problem, TAs are there. Another sorting problem. Just read it. So you have an n by n array of distinct integers having the property that aij is greater than equal to apq if and only if ai is greater than equal to p and I is greater than equal to p and j is greater than equal to q. So it's a configuration like this. I have an array which is n by n. I can mention that this side is n, this side also is n. And if I have an element here aij and I have another element here apq, then if I is greater than p and j is greater than q, then this element is greater than this element. Or in other, and it is if and only if. Look at differently, if I know that this element is smaller than this element, then I know I is greater than p and j is greater than q. This is the array given. And the problem is the same, and given some value k, can you search out in this array in an efficient manner? How will you do the search? There is an ordering, but that ordering is partial. It's not a linear order like that, where you have a strict order. Here is a kind of a partial order. So you have some kind of an ordering defined like this. Is the problem statement clear, or any question on the problem statement? No. Okay. So how do you do it? You will divide it in 4 quadrants. How?
First, I will search with A n by 2 position. That
First,
means middle of the matrix.
First, you will search with A n by 2.
Yes.
Okay.
If the key is bigger than this, then we will go to the 4th quadrant. That
what is bigger than this?
The key, that means the searching element.
Oh, the searching element,
yeah.
k. Okay.
K.
Okay, so let me try to draw it as somewhere here. So this is n by 2, 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 and you are talking about this element.
Yes.
Right?
Yes.
Now what is your logic?
If k is larger than this,
right,
then that means k should be there in the 4th quadrant. That means the southeast.
If k is larger than this, then what are you saying?
K should be there in the 4th quadrant. That means the southeast quadrant.
How? What if it is here?
No, it is not possible, because in that case the p is lesser than I.
Okay, right. Oh, okay. I think we'll need to relax this condition to make it interesting. What you are saying is, if this is the case always, then this is the 1 foot that you'll have to look at.
Yes.
Agreed. Now, okay, so let's relax this condition. Let's say that it is only in this direction, that if I is greater than or equal to P and J is greater than or equal to Q, then you have this. But you do not have the other side of the condition. Okay. Did you get his logic? His logic was that since we have both way condition, so it takes the center of the matrix and says that if k is greater than this, then it will mean that it belongs to this 1/4, because being less would mean that it belongs somewhere else. So it will simply look at this part. So I think the statement is to be read little differently. So please do not read this as if and only if. Read that if I is greater than or equal to P and J is greater than or equal to Q, then Aij is greater than or equal to APQ. And let us solve for that part. So now it cannot happen only here. It can happen here, here, everywhere. Any suggestions? Okay. if your item is, you'll compare with this element.
Yes, sir.
Yes, what can you say from that?
If the item is less than this item, if item is less than this particular element, then we will only consider the upper portion of the matrix and we will find the middle row among the upper portion.
If the element is
less than that element, that item,
less than that element,
yes, then we will only cover the upper portion of the matrix and there we will find again the middle row. Ultimately, we will get the row where that element exists.
So this is, let me think, this is A n by 2, 0.
Yes, sir.
Okay, so if I look at any element here, then I am talking about a PQ with the condition that P is less than equal to n by 2 and
Q can vary.
And Q
can vary from 1 to n.
Can vary from
1 to n.
1 to n.
Yes. And again we will find the middle row.
So your assumption is my given K is smaller than this or greater than this?
Suppose the item, the key is smaller than this.
K is smaller than A
n by 2.
N by 2.
Comma 0.
Comma 0.
Yes.
So
then for my remaining array, the last row will be n by 2 only.
And with that your assertion is that you will find it only in the upper half.
Yes, sir.
So if I have an element here, then what do I have?
The matrix will become now n by 2 comma n size, n by 2 into n size. And again I will find the middle row among 0th row and n by 2 row.
So if I have my ij here, then I have I greater than n by 2 and anything that I take here,
yes,
j is greater than 0. So anything that I take here will be bigger in this part.
Yes, sir.
Okay.
And once we come to that particular row where that element can, ultimately we will get single row where that element should exist. And in that,
no, I think rest of it follows. So you have a divide rule to do that, and so you'll keep on doing that till you come to a single row on which you do binary search. I think this will work.
There is a little modification of the previous logic, like rather than testing the horizontally, we can diagonalize it and test only the diagonal, and then we can sort in the lower triangular or upper triangular. Will it work?
But then what, you'll have to put the justification.
We'll have to test the element K with the principal diagonal elements.
But do they give you something that is on here, right? This diagonal.
Yes, sir.
Right? What do you get here?
So if the element is less than that particular element which is on the diagonal, then only test the lower triangular.
Why are you saying that? This does not work that anymore.
Will not.
This does not work anymore. His logic works because the choosing the first element in the middle row enforces that one of the indices are 0. So you cannot go below that. I think this will. What is the view? This will work?
Wait. Hello, sir. I think diagonal elements, binary search we can carry out for diagonal elements. Diagonal elements, if we search it first, and if it is less than that, we can come at the binary search again. So wherever nearby, if we get it row wise or that column wise below or front side, then only you are going to find.
Yeah, but that is kind of same as picking out the central element, right? Which lies on the diagonal.
Yes,
so
if the K is small, then we have to go again for diagonal only.
If you pick this up,
if it is
then you can say that this part of the array.
No, diagonally only have to check it. For that also. half again, half. Then diagonally, if that is greater, then we have to search only row-wise in front side and column-wise downside.
Okay, you'll have to write it out. I'm not getting the invariant of why other elements can be removed.
Because either row or column is smaller than that for remaining. For example, if you consider.
Yeah, but on the diagonal that does not happen.
No, diagonally only binary search, like binary search we are going for that. If it, for example, if k value is less than diagonal, then we have to search again diagonal only. Somewhere if you find k value greater than that diagonal. So
maybe it will work. I'll
for
have
example,
to
2.
work out, but I'm not seeing the logic right now. Okay. Yes, please.
If we search the middle row, then we search whether it is in the lower side or upper side. Next time, instead of searching for another row, if we search for a column, that will go on reducing our size of the rows.
No, it doesn't matter, because if I half it like this, I have the same number of elements. If I half like this, I have the same number.
On the row, we can get the middle point. Now, half of the element will be reduced.
No, in anyway you are removing half the elements. So whether you do it on row and then you do it on column, you will again do the same thing.
But we have to search only the 50% of the column rows only. Then we have half.
But the total number of elements is the same. Total number of attempts will be the same, because the number of times you can divide is log n.
Yeah, that's it.
So that will turn out to be the same. Yes, you are saying something.
Sir, we have to check k with a n by 2 comma n first. If it is less than a n by 2 comma n, then search for a.
Yeah, that's the strategy we discussed. So the smallest and the largest will have the same.
Yes,
that's a reflection strategy. That's a reflection of the same strategy. Okay, so there are several options coming out, and you could also think about what happens if I do this in higher dimension instead of 2-dimensional partially sorted array. If I have 3-dimensional or higher dimensional partially sorted data. Okay, let's pick another problem. Given a set of n integers, distinct integers, we need to partially sort the numbers to find the top k largest element. We do not want a total sorting. We want the top k largest elements in the sequence. Yes? You can build up a heap.
Sorry, out of linear time, max heap.
You can build a heap in linear time. How do you do that?
Build a max heap initially out of a set of elements. Initially a set of elements, we can build up a heap in linear time, I suppose.
From n elements. How do you do that?
Build up a heap initially, a max heap. We perhaps can do in linear time.
How? Almost. Almost complete or is complete? Heap is a complete binary tree. It's not almost. Yes. Yes. Yeah. Right.
See, you are at leaf level. Now you have built a binary normal array you are having, sir. So A of 1, A of 2 to A of n. So we know what are the positions of leaf nodes, what are internal nodes, because it is.
Right, we know that.
So we don't need pointers, all the story is not there. So now leaf nodes automatically that heap condition is satisfied. Why? Because it has no children at all. Okay. So second one is now go to the nodes which are second level, last but one level nodes.
Right.
Come down, second level.
Mm-hmm.
So now for that it will have either 2 children or 1 children or only 1 child. Now you compare with his children. If it is more, then swap it. Do only with one comparison, automatically it goes to leave position, then we are done with it. Now same thing you do for all last but one level. Next to go to the level which is above that. You keep doing. Now we are under assumption that it will be order of n log n. Why? Because we are taking that for each node we are doing order of log n comparisons are required. Why? Because the height of that corresponding binary tree is log n. But there we are over calculating. No, if we calculate exactly, so last but one level. So if your node is at level I, the number of comparisons we need to make is n minus I, log n minus I. If you take that into consideration, if you sum it, then it boils down to
Does
n
it?
into some constant.
It comes it that way?
Correct.
Okay,
It is
okay,
given in
good.
CLRS.
Okay. So then what do you want to do?
So linear time will get it, and after that is going to
Yes.
We may apply quicksort for the only kth element. So the complexity will be n into k. For just we'll sort with the help of with the help of bubble sort for the kth elements.
The first point is you are getting into solving this problem. Did you find out about the problem? Did you ask what is k?
No.
I'll say k is 2. You will do all of this, right? No. So the first thing you need to ask is k a constant? If k is constant, then what will you do? First k elements, right? K is constant. What will you do? K, that is the k largest elements we want to find out in sequence, and if k is constant, what can I do? You will find the largest, next largest. Yes? Mm-hmm. You don't need to, you have no impact of the number of elements on the list. But how do you know the first k elements has the k largest elements? We are looking for the k largest elements in sequence. How do you do that? Quick sort. Then with the quick sort, partitioning. How do you know that that this element will be in the kth position? So what is the complexity? Right?
Sir, in quicksort, using quicksort, take the first element to fix it in the proper location.
K is constant, madam. First we are solving for k is constant. K is constant. What will you do?
K is constant, sir. For example, 10. So I want to find out the 10 largest elements. So I take the first element in the quicksort, first element. I fix the pivot element in the proper location. I find out the location. The location is.
Okay, we'll do that.
Sir.
Yes.
Sir, one suggestion. If we break the list in k parts, and in each part we find the maximum element. So I think we get all the k largest elements.
That does not tell us that these are the k largest elements, because one part may have all the k largest elements.
Yes, sir.
Itself does not. Very simple.
Sir.
See, the first thing, if k is a constant, I can find max on the list k times, right? That is my answer. K times n, right? I don't need any. So it's order k times n that you can get it, right? So can you use any sorting algorithm to do this?
Sir,
Selection sort, yes. Bubble sort, right? So it's just changing the bubble sort. Selection sort will also do that. Bubble sort. Okay. Now, if k is not a constant, if k is not a constant, then what can we do? K is a function of n. Go for
Max heap. Hippie.
Huh.
You have to go for a re-hippie again and again for k times. If
So
we
that
are
will
deleting the topmost element, then kth time. If we have deleted kth time, then we will get the kth largest element.
So the complexity would be
Complexity will be k log n plus big of n.
k log n plus log
Big of n.
order n. Okay.
Yeah.
Now, anything else that we can do?
in quicksort, if we choose pivot, sir, here.
Where are you? Okay.
In quicksort, if we choose pivot as k plus 1, and we will keep
Pivot as k plus 1. How do you do that?
k is the element.
K largest elements I want to find out. K is not the value of the element.
Okay.
We want to find out the k largest elements in order, in sequence.
K largest element. That
K
means
largest
first 10 largest element in the sequence.
In that sequence.
So we can. I'm not sure about it, but just I'm telling. We have to choose. For example, k is 10. Then we have to choose pivot as 10, and we don't have to somewhere we have to stop the algorithm when only that much part is sorted.
In using which algorithm?
Quicksort.
How do you do that in quicksort? You have no control on that.
Somewhere we have to stop that in between when k.
No. That's like saying somehow we will have to solve the problem. Yes.
Sir.
By which algorithm? Select. Okay.
Sir.
Yes.
Here. Sir, we can improve that algorithm using that pivot, selection of pivot, making that pivot. If that position is the kth largest, then we will just stop it, pivoting in that median.
But that's just a matter of chance. It may or may not happen.
Sir,
No.
it will happen. It will happen.
How?
Because we are selecting the pivot within that.
How are you selecting the pivot? Please tell me that.
Randomly, first of all.
Randomly.
Swap with the right side.
Right. So you have randomly taken an element, made it the pivot.
Pivot.
It could be k. It
or
could be less than k. It could be greater than k.
Greater than k. Then, if it is less than k, we will shift to that left side. Then, less than k, we will shift to the right side. Then, we will skip again and again. It will give the big of
What is the complexity?
n. Big of n.
What is the complexity?
Big of n.
Big of n?
Yeah.
How?
Linear time complexity.
No. Every time you need to do that. Every time it is order n. How many times you need to do that?
Not every time.
Yes, because every partition is order n.
No, sir. First, you have to go for big of n. Then you will skip half.
How do you know you are skipping half?
Maybe or may not be.
You do not know.
Yeah, we don't.
So it could be order n again. It comes to that same corner case of quicksort, right?
Yes, sir.
Sir.
Yes.
This is the partitioning case.
Blue shirt.
Pivot would be n minus k then for the first time we'll get the largest element, replace that, and we'll take that largest element in a second array, store it, and replace in the original array with -1. And we will run this loop k times.
So that is k times n. Right, that is the first solution. That will work if k is a constant.
Sir.
But if k is itself order of n, then certainly that, or k is some function of n, then that's not interesting, because that will give you a quadratic complexity.
Sir.
Right.
Sir,
Where
here.
Can we apply cell sort on this?
Can we apply?
Cell sort.
Shell sort.
Yeah.
Yes.
So dividing the total thing into the different cells and apply any constant, apply any stable sort on each bunch of it, and then getting last 10 elements. It will give.
What is the complexity?
It could be it's proved that it takes n raised to 2 by 3.
We have one solution, I think, proposed here. That's one workable solution could be that, say, I have to do it for k. So, I have this array. I will use the select algorithm. Right, we did the select algorithm, which finds out the kth largest element or kth smallest element from an array, unsorted array, in linear time. So, we have that here. This is the kth position, and if this is decreasing, then this is the part of the array that needs to be sorted. So, if I have done this selection and I use that select element, say key, as a pivot, then I will be able to get all the k elements on one side, and then I just sort on that part. So, this will be, what will be the complexity? Complexity of select, complexity of partition, right, and then the complexity of sorting the selected numbers, right. So, now if k approaches n, then this will basically approach the sorting of the whole array. But if k is smaller than n, much smaller than n, but not a constant, then this will certainly give you a good performance. There could be better ways of doing that, of course, because that's
Sir.
It's certainly always an open question. Yes.
Sir, can we do it like this, that we want to find out the top k elements? So we will divide the array, we will use the quicksort n by 2. Okay, and when that n reaches to k, we come to know that
how will you divide? How will you divide?
N by 2, we divide, we will find the pivot as the middle element, middle position
How
of
do
the
you
array.
know that pivot value?
For example, array is 1 to 100, the middle will be 50.
Right.
Okay, we will keep 50, the larger will be on the higher side of 50.
How do you know that element? How do you know that element that has to go at the location 50?
Okay. So we have to, we can use a median for that purpose then.
Okay, you have found the median, yes.
Then apply the, find the median, use that as pivot, sort across it. Then again, if we want that
But
median is.
I mean, the moment you sort across it, then you are basically into n log n complexity.
Sir, if that median is larger than k, then we have to still follow the algorithm. And
Yeah, we are doing better than that, because we have found the kth position itself, because select will give you the kth element itself, and that too in linear time. So certainly that does better.
Okay.
Because you use select to find the key that is the kth largest in this array. So use that and place it in the partition.
Okay.
So naturally one side of this are the output elements.
Right.
So you
Yes,
have
sir.
the k largest elements already.
Yes,
The
sir.
remaining part is to put them in sequence, so use a sorting on them.
Okay.
Okay. Right?
Digits in the number, all the numbers are constant.
Digits in the number are constant. I did not really think about it. Yes, please.
Now,
Let us assume it is not constant. Let's say.
If it is constant, then we can go for Reddick sort also.
Yeah, but this strategy will work for sorting humans also. Right? So, I mean, we are in the paradigm of comparison sort. If it can be compared, it can be sorted. So, with radix and all that, things will become different. I think should we do this or what is the time? Let's do this last one and close it. So, I think this is also very straightforward. Is count? You are familiar with what is called an inversion. Inversion is a pair in a list which is not placed in the right order so far as the sorting order is concerned. So, say if we look at this array and if our sorting order is say increasing, then we find pairs of elements which are not in right order. For example, 2 and 4 are in right order, but 2 and 1 are not in the right order. The 1 should have been to the left of 2, or 4 and 1 are not in the right order. Whereas 2 and 3 are in the right order, but 4 and 3 are not in the right order. Right? So, as many pairs as you find that are not in the right order is called the number of inversions. So, inversion is an interesting way to look at any sorting problem, because what will happen? If the array is sorted, then how many inversions you have? 0, obviously. And if the array is sorted in the reverse order, then certainly you will have maximum number of inversions. So, what we want to find, given this, we want to find out whether we can count the number of inversions. So, you need to do an algorithm by which you can count the number of inversions.
Sir, find the largest element.
I mean, it's good, but I'm looking for someone who has not spoken.
Sir, apply merge sort. Hello, yes.
Yes.
Apply merge sort. Modification of merge sort.
Apply modification of merge sort.
Merge sort. It's a kind of merge sort. Partition the complete.
What can we? I mean, can't we do anything simple from here? Can't we just like?
See, my approach will have an LGN complexity.
Can't we do something simple at this stage? Yes, blue T-shirt.
Count with 0, and while swapping we will increment the value of that count with 1. So we will get the number of counts.
Can't I, what is the complexity of this?
It will be again n square.
N squared. So that's like, I can just do this, right? I start from this element, go over the array and find how many inversions exist. Start from the next element, go to the right, find how many inversions exist, right? That's n squared. Anything better than that? Pardon? Right? Please speak on the mic.
While doing the merge procedure, we have two arrays, one is left one and the other one is right one. If the element at the head of the right array is greater than the element of at the head of the left array, then there is a inversion.
And if it is not?
If the array, if the number in the left half is smaller, then there is no inversion.
It just depends on the head of that array on the left array, is it?
Yes.
Suppose that the head of the array on the left array is smaller than the head of the array on the right array.
Yes.
Then what
Then
happens?
there is no inversion.
Then next?
There is no inversion.
Then what do I do? No inversion for that whole. Let us say this is what you are saying, right? So, this head, this is the position when I am merging, and the left and the right arrays are sorted. So, I am comparing this with this, and sure there is no inversion then. Then
Now there is an inversion, that is, if this is, we are having the left pointer is I, we are incrementing I, and the right one is j, then that is mid minus I, we will be increasing the number of inversion by mid minus
so
I.
I can say that if this element is greater than this, then all these elements
Yes, will be included in the number of
is
inversions.
greater than this,
Yes.
right?
Yes.
So, all the count that exists, that will be greater than this, and I can just increment by that count. So, with this problem can be solved in, what will be the complexity?
N log n.
N log n, right? Can you do better than that? Pardon? Insertion sort can work in order of n log n. How?
Sir, when we want to find the position of element, we need to compare. If the element is less than the previous one, it means there is one insert. We have
Agreed.
to count increase.
No, how can it work in n log n? That is my question.
Insertions. Because maximum time it needs to compare is order of n, means in worst case insertion sort is order of n log n actually. Maximum comparisons. We need maximum comparisons.
The last question will close with, can you do better than this? Can you find insertions in less than n log n time? Yes?
Something. So, if there is an inversion, then take the advance the other vertex, keep this advance the other index, keep the other index same, and keep on doing it.
Yes, but that gives you certain pairs. It does not give you the other pairs. You're doing from this to this, but it does not give you between these. Because when you have started from two sides, this has scanned over, this is scanned over, but what is scanned over, within that the inversions will not come in, right? So, it's an interesting problem to think whether you can do inversions in less than n log n time.
We can use the rank of the element also.
Pardon?
By finding the rank of elements.
Tell the algorithm. I do not know such complicated algorithms. Tell the algorithm. What will you do? Tell me the strategy. Question is, we find that we can do n log n. Can we do better than n log n? That is the question.
Sir, if we can do better than n log n, then sorting time also that better than n log n.
Sorting time also?
Sorting complexity will also be a better n log.
Why do you say that?
Because it's totally depend on sorting.
Mm-hmm.
Sorting. This is so what? Displacement of the elements. That means it is unsorted. If we are finding that all unsorted pairs in that better algorithm with that n log n, then that means it implies that its sorting time also better than n log n.
But these two things are, you'll have to build up a solid logic on that, because
yeah,
these two things are different. Yes, one is just counting them. For example, when you are counting it here, we are not doing anything with them. It's just the index difference which will tell you that. When you sort, you will actually have to move these elements.
Yes.
Right? So this is different. So this is somewhat like saying that I have a rectangular wall and I want to find out what is the cost of getting it painted. Right? I know the height, I know the width, I can find out the cost in constant time. But to paint, I need the quadratic time because I have to go over this. So it's not always that if you can measure, it is same as the task. So I will leave it that question. If you have difficulties, ask the TAs that can you do inversions in less than order n log n time? Or what is the lower bound of finding inversions in a list of n elements? We are out of time, so I'll close here. I have some more problems we'll discuss in the second half. Thank you.